Each wave fluctuates with a phase, something that defines its timing. And here we relate the phase to frequency and wavelength in vacuum. We have two light pulses initially in phase despite the delay. In the space-time of overlap we have the interference. This interaction is typical of waves and allows them to share their space-time. These two waves are in phase, so the delta is zero and the interference is totally constructive. This overlap affects how an external system interacts with that space-time interval. It is no longer an independent action on each wave, but a linear sum of the two. On the opposite, when the phases are 180 degree shift, we have destructive interference, meaning that even if here I locally have two waves, the overlap of the phases compensate each other and my detector will see nothing. When the two pulses don't have delay, 180 degree of phase shift will cause total destructive interference and no detection. And with 0 degree, interference is constructive. Phase shift is a qualitative effect. It doesn't directly slow down the speed of light, but is a change in the shape of the wave. Degrees of phase shift between the two extremes create a gradient of results, but there are a lot of video well made about this topic, so now look at interferometers. I have two light pulses collimating into a beam splitter before reaching the detector. If the resulting waves are in phase, the signal will be stronger because interference is totally constructive. If I manage to change phase on just one of the pulses, the detector signal will change accordingly because of interference. Increasing the gap between phases makes the signal weaker and weaker until 180 degree phase shift where nothing is detected. Since we are using one single emitter, the same signal is traveling two ways. If my setup is accurate, I can have two paths with the same exact length, and when the two pulses meet again, they are still in phase. Interference is totally constructive, so the detected signal is almost identical to the initial one. This is useful as a point of reference, a clean final signal. If at some point I detect fluctuations, it means something occurred along the path and shift the phase because now I have some degree of destructive interference that pollutes the received signal. Gravitational wave detectors are example of B-scale interferometer. Moving this part here and adding a detector near the emitter, we match the appearance. In this case, these two arms should detect spacetime fluctuation from gravitational waves. The role of the beam splitter is to separate incident light beams, but each spacetime change of the wave affects the phase too. So while half of light is transmitted unaffected, the other half is deflected by 90 degree. So here phase 2 is 90 degree shift, and the two pulses are now 90 degree out of phase. This effect is not a property of beam splitter. It's true everywhere we have angled interactions, so the phase shift must be considered because it drastically affects the following interference and detection. All interactions mirrored on both paths don't affect the results because even if phase is delayed, the effect is symmetric. So to have path 1 equal to, we need the same length and symmetry. Following the interferometer, we can now ignore the two mirrors and reach the second beam splitter. Here we place two receivers to see what happens. Since the beam splitters separate each pulse, after the second beam splitters we have 4 pulses on 2 paths, and we must be careful on how phases are mixed. Waves can be linearly summed, so we start with path 1 and see that signal to detector 2 is transmitted unchanged, while to detector 1 has a 90 degree shift. Signal on path 2 already has a phase shift. So to detector 1, the pulse is transmitted unchanged with a 90-degree shift, while the deflection toward detector 2 add another 90 shift, totaling 180. Putting the two together, we have on detector 1 two pulses with the same phase, and they constructively interfere. Toward detector 2, the waves are 180 degrees out of phase, so the interference is totally destructive. Despite the theoretical presence of waves, nothing is detected here. If we place an obstacle on this path so that no light can be transmitted, becomes pretty clear why phase doesn't matter, and light from just one path will be split and detected in both receivers. Everything said until now is according to classical determinism. We can figure quantum mechanics thinking at the same behavior, but the blueprint is done by Escher. Wavefunction teleport probabilities and collapse to finally get the same results. But only one of the two is breaking physics. One logical contradiction of quantum mechanics has not been faced yet. As we saw, light in two paths shares some correlation as the phase. But interference is possible because we have distinct and independent systems. In quantum mechanics, the wave function is still one, so when the two parts meet again at the second beam splitter, the interference we can measure comes from one fundamental system that can do work on itself. And this is a logical and physical short circuit. It's like saying an electron emitting a negative field has this part of the field repelled by this part. Or roughly, you can't push or pull yourself. Interference comes from multiple entities, while this amplitude always refers to one single system, even when is spread. Yet, instead of merge again, these probabilities can somehow interfere. If the wave function evolved this way, we can see how it spread. But on reverse, when the wave function converge, there is no equivalence. Despite being still one wave function, self-interference can somehow emerge. And if this is not enough, we are talking about a complex, non-local, undefined wave function, which is capable of localized and finite interaction with the external system and even with itself without collapsing. As with interferometers, the same flows are with double slit experiments. These are okay for classical optics and easily explainable with determinism, but are impossible following quantum mechanics because of its own rules. The wave function is still one, but we have uneven interactions and self-interference, while collapse is still the detector. Another important aspect of experimenting with light is related to polarization. Waves considered until now were genetic fluctuations, but they can be polarized circularly or with a specific angle. If a light wave circularly polarized hit a polarizer that is vertically aligned, the wave is transmitted with a vertical polarization. Waves only have 90 degrees to match the difference. There is no up-down, so rotate 180 degrees. A vertical polarizer doesn't affect the results. A circularly polarized light hitting a vertical polarizer is only partially transmitted with vertical polarization. Every time the polarization of incoming light doesn't match the polarization of the filter, some amplitude is lost in transmission. In a vertically polarized light that goes through a 45-degree polarizer, just half of the amplitude is transmitted with the new polarization. And with 90-degree difference, no light will be transmitted. Polarization is as important as phase to determine the interference outcomes. If two waves have the same polarization, Phase define how they merge. But when the two waves have 90 degrees of difference in polarization, interference cannot occur, no matter the phase. And here too, in polarization, there is a gradient in between, as with the phases. To summarize, interference between waves depend upon phase and polarization, and these two factors fundamentally affect outcomes and detections. In waves, we can have qualitative interactions that affects, for example, the phase, and quantitative interactions that affects the amplitude. Waves, from the view of a human, have very weird spatial behaviors. Two incident waves just temporarily interfere, because in absence of material interaction they will keep the direction unchanged, and they will be identical to the previous waves, as interference never occurred. Each second in any spacetime there are uncountable interferences. The light we see from the panel had billions interferences. Each device, monitor, antenna, star is emitting waves, but they intersect without influencing each other. We know this since we don't see any artifacts caused by these overlaps. All interferences leave no mark in the picture. It's trivial to say radio interference does not depend on which waves the signal encounters on its path, but from which waves it receiver. Indeed, the receiver 2 could detect a signal that receiver 1 can't. The detected interferences are not into waves. They emerge in antennas, absorbing more signals at the same time. I call this local and kept the difference with observable because local condition is temporary. We just saw how many interferences can occur before the observer. Waves do not influence each other. Each system is moving, conserving its properties, even during destructive interference. The same is true in different waves traveling the same path. It's a space issue. Here we have a wave packet where different waves are superposed, each one with its own phase and frequency and creating an overall amplitude. But each wave is independent, so all energy is coming from some direction and is going somewhere, keeping its own states. Even if this is what we can observe, waves must share their space-time without consequences. While local interference do not affect the waves, interaction with matter can transform that energy and make permanent a temporary state. When the receiver absorbs the wave, such energy is no longer free propagating because it is now part of the fluctuation of a particle as the electron. Before the wave packet's dispersion, the white light we could see is made of multiple frequencies. They share the same spacetime, but they are not fused together. In dispersion is shown the independence of interaction of what is superposed but not bounded. And here we have an hint on quantum mechanics collapse of the wave function. These free propagating waves represent energy distributed over many frequencies and sharing the same spacetime interval. Considering this representation, the equivalent of all these waves in superposition, and picturing the wave packet this way, we see that optical effects can be both qualitative and quantitative interaction, but they keep the system a free propagating wave, as with interferometer, double slit, and polarizers. Even if I have a material interaction, the wave is still free. Detection is where energy of waves is absorbed and transformed, so that is no more free propagating and it is energy in some particle. In wave collapse refers to a quantitative interaction with matter that transforms the energy of waves. With detection and observation, we are freezing a temporary superposition, and we see the overall combination in the form of wave packets. Free propagating waves can only change because of interactions with particles. Interference is the physics between waves, from radio to UV and beyond. Individual characteristics are not important in the concept. Waves can interfere but do not interact, so that the overlap has no consequences on them.